Okay. Okay, so here we go. Let's integrate. Okay. Integrate. I'm just going to give you some problems, and we're going to work on them together, and we're going to learn things that we need to learn. X to the third minus 2x dx. Okay, let's integrate that. This is what's called a definite integral. Okay. This is called a definite integral. So how do I do this? Just do the normal, right? So we would get x to the fourth over 4 minus 2x squared over 2, right? We add 1 to the exponent, and then we divide by that exponent. It's the opposite of what we do when we do the derivative. The derivative, we bring the exponent in front and multiply, and we subtract 1 from the exponent, okay? Okay, so we've got x to the fourth over 4 minus x squared. We are evaluating that. We use the vertical line from -1 to 2. Now, part of your fundamental theorem of calculus says that the integral from a to b of f of x dx is equal to f of b minus f of a. There will most likely be multiple choice questions where you need to specifically use that definition, okay? And I'm sure we're going to see those, but that's your basic definition. So that means, okay, coming down here, we're going to do, make sure you use parentheses so you don't lose track. We're going to substitute in the 2, the top number, 2 to the fourth over 4 minus 2 squared, right? That's the f of b. And we're going to subtract f of a, which will be -1 to the fourth over 4 minus -1 squared. Okay, that's the f of a. So all I did was substitute them in. Okay. So this gives me 16 over 4 minus 4 minus 1/4 minus 1. Sixteen over 4 is 0 minus -3/4, which equals 3/4. No, that's not my c, because this is a definite integral. Good, I'm glad you said that. This is a definite integral. There is no c. Notice there's no plus c, because I'm going to be able to determine what it definitely equals because I've got an upper and a lower bound, okay? What's happening here, and again, we've really skipped through a lot of stuff and we're just covering it as we learn it, okay? What's happening here is I've got this curve. I don't know what's it look like. Let's see, x cubed minus 2x, right? Let's see what that looks like. X cubed minus 2x, and we'll go from -1 to 2. Okay, so I'm going through 0. Okay, so I'm kind of going like this, right? Something like that. Okay, maybe not quite as curvy, right? So what we're doing is we're finding the area between the curve and there. So we're finding this area here, the integral from -1 to 2, okay? And that equals 3/4. Okay, that's what we call a definite integral. Okay, Now, we can also check this on our calculator because this is really nice, especially this was a pretty straightforward one, but sometimes when they get complicated, it's helpful to check it on our calculator. So let's do that. Okay, take your calculators out so that you do this and remember how. So we're going to go to math. And instead of choosing n-deriv, we're going to choose FNINT. Basically function integral, number 9. Okay. And we're going to go from -1 to 2. You can only do this for a definite integral. You can't do it for an indefinite. So the ones that don't have a lower and upper bound, you can't use your calculator. Okay. Now, I already have the function in y1, so I can just choose y1. If not, I could type the function in right here. Okay. And then with respect to x, and there we get our answer, 3/4. Okay.
So you just put the original function. Oh, okay. I got it.
Okay. Can I graph?
Just put that.
Let me see if I can graph it. Let's say number 9. So let's do it again. I don't know if this will graph it as just 3/4 or if it'll actually show me the shaded area. I'm not sure. I think it's just going to graph it as 3/4. But let's check it out. Yeah, just grass it. I feel like there is a way of doing that. Oh, wait a minute. I have an idea. Wait.
Isn't there a shading option?
Is there a shading option?
7 shades.
Yeah, but I don't know what I'm shading. So yeah, okay. I won't waste time on that. I'm pretty sure there's a way of doing it, but that's okay. All right. So let's look at the next one. Okay. So it says the graph of a function, okay? The graph of, I have such bad eyes. God, give me bad eyes. Okay, the graph of f is decreasing and concave up. So make sure you're copying this down. Decreasing and concave up on the interval from 0 to 5. Which of the following must be true? Okay, so f is decreasing and concave up. That means that f prime is less than 0 and f double prime is greater than 0. That's what comes to my mind right away. Okay, so number 1, a left Riemann sum approximation of f on 0,5 is an overestimation of the integral from 0 to 5 of f of x dx. Okay. Is that true? If it's decreasing and concave up, right? So let's just kind of sketch a little example. This would be decreasing and concave up, right? So a left Riemann sum, right? So that means I'd be looking at the left corner of the rectangle. Okay. So is that true? Yes, that would be an overestimation. Okay. So that we think that that's true. Okay. Selection number 2 says a right. Okay, I'm not going to write it all about, but a right Riemann sum is an overestimation. Well, you can't have both of those true, correct? So a right Riemann sum is basically going to give you this. So is that true? No. So number 2 is not true. Okay. Number 3, trapezoidal is an overestimation. Trapezoidal. So let's see. Let me just redraw it again because it's hard to see mine now. Okay. This one's a little trickier, isn't it? Okay, so let's draw our trapezoids in here. Okay, so, okay, there's a trapezoid. It's kind of a tough one, isn't it? That's a little bit unclear, right? So I'm going to draw a more severe curve so that I can be more certain about it. How about that? Right.
What do you mean?
What do you think?
Slightly over.
I think it's an over. I think you can even go more severe. Right? How about this one? Right? And here's a trapezoid here. Now we can really see it. Definitely an overestimation. Okay? So our choice is 1 and 3. Okay? If you're still not sure about the trapezoid, sometimes think about the opposite of that. Let's draw one that's doing that. Now let's draw our trapezoids. Right? Look at that trapezoid. That is clearly an underestimation. Okay? So that kind of solidifies the fact that it's an overestimation when it's concave up. Okay? Questions on that one? Okay. Next one. The rate of change in the depth of a reservoir. Okay, again, please copy these down. Okay. The rate of change in the depth of a reservoir how do you spell reservoir? ER. In feet per month is given by R of T. Okay. T is measured in months. What are the units of the integral from A to B of R of T dt? Okay, let's think this through, right? If the rate of change in the depth, so we're going to say d, change in depth with respect to time, is measured in feet per month, right? Okay, so if I take the integral, right, the rate of change in the depth is given by r of t. If I take the integral of r of t, what am I getting? If I take the let me put it in terms of something that you're familiar with, right? We know the derivative of a position function is equal to what? Velocity. Okay? And velocity is typically in something like maybe feet per second, right? Okay. So if the derivative of position is velocity, what's the integral of a velocity function? The position function, which would be in what unit? Feet. Okay, think of it this way. I'm integrating feet per second with respect to time. dt, change in seconds. What's that equal? Feet. Does that make sense? So now go back up here. If I integrate r of t, which is feet per month, we're going to get feet. Okay. What if I were to integrate an acceleration function? What would I get? I would get a velocity function, which is feet per second. Good. Everybody okay with that? The question was asking what the units of this integral would be. So that, and your choices are feet, months, feet per month, or feet per month, right? Is it feet? Is it months? Is it feet per month or feet per month squared? It is feet. Okay. Oops. It's not the velocity. I was using this as an example just to get you thinking the right way. But it says that R of t is the rate of change in the depth of the reservoir. That's what R of t is. Rate of change, that's equivalent to what we think of when we think of velocity. So this is just an example to help you think along the right track. And a lot of times I do that. I'll go back to my position, velocity, and acceleration that I know about because that's my comfort zone. I go back to what I know to figure out maybe what I don't know. Okay. Okay. So this is a hard one. We've got the limit. I'm going to let you work on this for a few minutes. The limit as x approaches infinity of the summation of I equals 1 to n of 2 over the square root of 3 minus 4i over u. I'm sorry, over n. Why did I say u? What in the world? Where u come from? Over n times 1 over n. Okay? And the question is, which of the following integral expressions is equal to that? So, is that equal to the integral from 0 to 1 over of 2 over the square root of 3 minus 4x dx? Part B. 0 to 1, 2 over the integral of 3 minus x dx, c 0 to 4 of 2 over the integral of 1 minus x dx, and d, the integral from 3 to 4 of 2 over square root of negative x dx. Okay, copy that down. And I'm just going to remind you that the limit as n approaches infinity of the summation of I equals 1 to n of f of a plus delta xi delta x, okay, this is your integral from a to b of f of x dx. Okay. And remember, delta x is equal to b minus a over n. Looking at that, is there one that you can eliminate right away?
Yes.
Which one?
C,
Why?
because B minus A is
Right. This is my b minus, this is my delta x right here. So b minus a has to be equal to 1. So I can eliminate c. Okay? Okay. So what else can I do?
You can eliminate D.
Why?
Because it wouldn't be. Because you'd be number 3. 3 minus, correct? So then it's not in the change.
Yeah, so I'm looking for, at this point, right, what's my f of a plus delta xi, right? F of a plus delta xi, that's 2 over the square root of 3 minus 4i over n, right? So, and my a, well, my a is either 0 or 3, right? So that means we can definitely eliminate d, because I'm not going to get 3 minus 4i over n as negative x, right? Okay, so then how do I choose between a and b? I'm going to let you work on this for a few seconds. Don't just sit there and look at me. Shh. Let everybody work on it. Huh? Turn it off?
Thank you very much.
Mm-hmm.
I'll just get the little. It worked to do its job.
Okay, so let's talk about this a plus delta xi. What's delta xi? That's going to be the 1 over n I, right? We know that because delta x is right here. This is my delta x. So delta xi is 1 over ni. So that means a, right? It could be 0, right? It could be 0, or it could be 3. Oops, but we eliminated 3. Sorry. A is 0. All right. So A plus 1 over Ni. Okay. So let's see here. Where can we go from there? Plugging it into what?
If you know,
Yeah. Go ahead. Say it again.
you would plug it in, you know the original equation.
This is 1 over Ni. So let's plug it in here and see if we end up with that. We end up with 2 over the square root of 3 minus 4 times 1 over Ni. Well, that sure looks like that to me. If I plug it in here, I'm going to get the square root of 3 minus 1 over Ni. So this looks like that has to be the correct choice. Yes.
Couldn't you just because we already said delta x was 1 over n. So couldn't you just say that it's b minus a and then look at all the problems and realize that the only one that we didn't cross out for b minus a being 1, ba?
Well, letter B minus A would also be 1.
Right, but we ruled that one out at the beginning.
How did we rule that out?
We didn't?
I don't think so.
No, I'll just see.
Did we rule out c?
We ruled out C because of the B minus A. We ruled out D because of the negative X.
Okay, that makes sense. I just crossed off the wrong one.
Yep.
I didn't know why we crossed off.
That's fine. That's fine. Okay.
Locura de Barça. Armando.
Okay, I'm going to skip this one because it's a graph and it's going to take me too long to draw the graph for you.
Do you have to hear her songs all day long, Smurf?
Oh my goodness.
Yeah, it's her Locura de Barça. She does like a Montreal style bracket with all these different Spanish songs and all her
Actually, really
dances.
fun.
It was kind of fun, but now that she's up here, it's like.
It is very loud in this building. We really need to do something about it. Okay. So we've got the integral, the negative 1 of 1. Okay, copy these down. Okay. So the question is, if the right Riemann sum approximation
Why is it right?
of the integral from negative 1 to 1 dx with n subintervals of equal length for a continuous function f of x. Right, so it's giving you all sorts of important information. If it is 3n times n squared plus 5 times 4n plus 1 divided by n to the 4th for all n then the value of the integral from negative 1 to 1 of f of x dx is A is 3, B is 12, C is 54, D is 90. See if you can do that. Are you having trouble?
No.
Don't know where to start, do you?
Exactly.
Okay. Let's just talk about the Riemann sums, right? Riemann sums, right? If we have these rectangles, okay, by taking the area of each rectangle, and adding them together, right? That's what we do when we do Riemann sums. We take the area of each one and we add them together. What does that ultimately give us? The area under the curve, which is an approximation of the integral, right? Now, if I double the amount of rectangles, what can you tell me about that approximation of the integrals?
More accurate.
Okay, so if I continue to double it, get more and more and more and more and more rectangles, then the approximation becomes closer and closer, right? So in theory, the limit as the number of rectangles approaches infinity is actually going of that function, right? Is actually going to be equal to the integral of that function, right? So here we have the integral of equal length for a continuous function is, right? They give us the function. What do you think we need to do with that function? Take the limit as what? Or how about n approaches? N approaches infinity of 3n times n squared plus 5 times 4n plus 1 over n to the fourth. All right, going back to limits. So, well, let's see. What's the numerator look like? It's approaching infinity. So, what's that numerator? We've got, if we were to multiply that out, what's that first term going to be? N to the 2, okay, something to the fourth. And then we've got a 3 and a 4 here, so that'll be a 12 n to the fourth plus, who cares, right? Over n to the fourth. So that equals 12. So if I approach an infinite number of rectangles, then it looks like my Riemann sum is actually going to be 12. So that looked like a really hard problem algebraically, but it really was more a calculus theory problem. You had to recognize what we were representing the integral with, okay? Okay, this is another graphing one, which I'm going to skip. Get up. Something you would not expect to hear in a math class. Get up. What could possibly be happening that you have to say to your high school students, get up?
Or sleep.
What could be happening? All right. Let uppercase F be the function. Okay, these are excellent questions. These are the types of questions you're going to see on your AP exam. Okay? Yes.
Can you remind me what the difference between lowercase and uppercase f is?
Yes, uppercase F is the anti derivative of lowercase f.
Right. Thank you.
Okay. It's given by, be the function given by uppercase f of x equals the integral from 2 to x. See, uppercase f, right? And the integral is the antiderivative, right? Of the natural log of t plus 1 dt. Which of the following represents f prime of x? We've got choice A, 1 over x, choice B, 1 over x minus 1/2, choice C, natural log of x, choice D, natural log of x plus 1. Anybody know? Ben,
I'm gonna take a stab and say D,
why?
because it looks like the function inside.
Because it looks like it?
Yeah.
Okay.
I'll say the same thing.
Anyone else? Okay.
Say capital F log of x or lowercase f?
Capital. Okay, the second part of the fundamental theorem of calculus, the fundamental theorem of calculus, part 2, says that the derivative of the integral from a to x of f of t dt equals f of x. That's the second part of the fundamental theorem of calculus. That means that it's that one.
My bad.
Let's go.
Okay, so the key parts here, the key parts to recognize, first off,
It's just like,
that this is a constant. The lower limit is a constant. The second key part is that the upper limit is x. Okay, as soon as you see that, you should start thinking fundamental theorem of calculus. Okay, now the other hint is, right, this is x, but this is t. And that's the trick there. Like when you see that you've got f of x, right, we said uppercase f of x, but this is all in terms of t. So that's another hint that we're doing that. Okay, and they're actually so simple when you see those, right? Sometimes we like to make things complicated, but it's really it's that simple. Okay, let's see here.
I was thinking that was
Um, boom.
we're meditating.
Can you tell?
I need brain break.
Oh,
Oh.
good tone. Okay, we're gonna skip that one for now.
Let me see what I got.
All right, let's do this one.
If I was trying to at the beginning, I definitely could hold it all under,
Here we go. We're gonna
but
take
no.
the integral of 4 over x squared minus tangent x dx. Now, I want to start, we're going to start being really picky about your notation and your terminology, right? We have to speak calculus speak, right? We have to speak calculus speak on our AP exam. So, in other words, if you did this, you would get points off.
How dare you, sinner?
Okay? Why?
Because it's
'Cause it's saying-
Right, this is implying that it's just the tangent x times dx, right? It's got to be the whole thing, the whole function, f of x. There's my f of x right there, right? So we have to make sure we speak calculus, okay? Okay, let's integrate this. Okay, you can do it. I'm going to let you do it. I just realized I may not have given you something. So, oh, shoot. Did I give this to you? I did not. Darn.
What?
Okay. You can't do this one.
Let's just be on time.
Why can't you do this one?
Because you can't integrate.
You don't know the integral of tangent. Yes. So that reminds me, so looking at this problem, I'm going to rewrite this first off as 4x to the negative second minus tangent x dx. Okay. All right. So what's the, sorry. Okay. So let's take the integral of 4x to the negative second. So we're going to do what? Add 1 on top, so that becomes negative 1, and divide by negative 1, okay? Minus, now what was the integral of tangent? Negative, no, not negative natural log. Isn't it natural log?
No, it's negative natural log.
Oh, I'm sorry. Okay, sorry. So this would be a positive natural log of cosine, and this is just x, so cosine x plus c. Was that one of our choices?
You didn't give us choices.
Oh. Well, that is one of our choices.
So that's the answer.
So this is going to be negative 4 over x plus the natural log of cosine x plus c.
Wow.
Okay. Our choices were A, 4x to the third over 3 plus natural log cosine x plus c. B was negative 8 over x to the third minus secant squared x plus c. Okay, and then choice C, choice C was negative 4 over x minus secant squared x plus c. Let me show you that we could have gotten the correct answer on this without knowing the integral of the natural log of cosine x, okay? Look, first off, we can eliminate choice A and B because we definitely know how to integrate 4x to the negative half. Negative 2 rather. So we eliminate choice A and B, leaving us with a choice C or D. Here's my choice D, right? Well, if I look at this, I just have to recognize that the integral of tangent is not secant squared. Right? The integral of tangent is not secant squared. How do I know that? Logan. That's the derivative of tangent, right? Okay, everybody paying attention? Okay, so even if I didn't know the integral of tangent, I know that it's not secant squared because the derivative of tangent is secant squared. Therefore, the integral of secant squared is tangent x. So that's backwards. So based on that, it has to be choice D. Yes.
Could you also find it because by rewriting tangent as sine over cosine, and then that's how you would know that it's cosine,
Absolutely.
because the
Very
u-substitution.
good. Very good. Okay. So yes, we could, but again, saving time on your test, right? Integral of tangent x dx. Okay, let's rewrite this as sine x over cosine x. Okay, let's think through this a minute. Okay, so if I were integrating sine x over cosine x, how would you do that?
I would make cosine my
Make cosine your u. Excellent. Cosine is u, so du is negative sine x. Okay, let's work through this because some of you are really having a hard time with the u substitution thing. Okay, so what we're doing is we're saying, okay, I'm going to write this as 1 over cosine x times sine x dx. Okay. So basically, we're saying, okay, I'm going to make this my 1 over u, and I want to make this my du, but I need a negative sign. So I need this to be negative, which means I need to put a negative outside. Everybody follow me? So now I have 1 over u times, this is my du. So if I'm integrating 1 over u du, that one I know, that's the natural log of u, which is the natural log of cosine x. But don't forget, we have a negative in front here, so that's negative natural log of cosine x. So even though we didn't memorize it, and that's why I say I don't have them all memorized, okay? Yeah.
I have a math question.
I figured that because
How would you take the limit of like cosine x if x approaches infinity?
the limit of that's not,
Yeah.
there is no limit of that. Well, no, this there is. It's going to be as x approaches infinity.
the highest number it
Hold on a second.
As
I
long
got to
as
switch gears. Limit as x approaches infinity of cosine because we're going from -1 to 1 and we're repeating. So I feel like that's,
like I want to say it's 0, but I know it
Wouldn't
can't
it
be
be
because
1?
I'm doing like nth term test for divergence, and I know my other two answers are right. I'm not too sure.
I was going to say it's oscillating, but it's not really oscillating. It's oscillating would be that it doesn't exist. It is 1.
It's 1.
You told us that.
Good job, Keelan. You could be in BC. Did you just say settle down?
Do you want me to show you the problem or?
No, that's okay. Hold on a second. Oh. No, I just Googled it and I'm getting that it does not exist.
D&E. You could be in BC. Right back there, you go.
Yeah.
Do you remember anything about series?
Let me stop the video here. Hold on a second.
Lit.
Oh wait,